as I alluded to in the last video, and if you didn't already watch the video on the basics of the definitions of continuity and identifying continuities, right, you need to go back and watch that. In this video, we're going to look at how to do it without a graph. Okay, so I have some examples here which I've typed up from past years, so I'm going to just talk our way through it and then do an actual example. Okay, the directions here say find the points of discontinuity for each function, state the type of discontinuity, and show proper justification for your answers. Okay, so we have this, right? Find the discontinuities. Okay, we remember this one has a domain restriction at x equals -3, right? So that's what I would do first, right? We consider that domain restriction. We got x equals -3, right? So this would be a point discontinuity. Now we need to classify this. Oh, by the way, if I said justify the discontinuity, right? How would I know that this is a discontinuity here? You could just say f of 3 has no solution, and that would be justification for the discontinuity, okay? And sometimes you'll be asked for that. It will just say identify the discontinuity and justify why it's discontinuity, and that's all you have to do. Okay? So now, with the directions here, it says state the type of discontinuity and show proper justification for your answer. Okay. So the first thing I think of as I try to justify it is this a removable or a non-removable? Well, I know it's non-removable, right? Because, well, actually, let me calculate my limits, and that this comes down to two methods. You can either sketch a graph of it and look at your graph, or you could calculate your limits to do it. But if you sketch the graph, then you can do the limits without actually calculating it. If you sketch that graph, you know what these graphs look like, then you can say, you can just give me that graph, and then just say, this would say, oh, it's an infinite non-removable discontinuity, okay? So just to be clear, right, if you think of it, there's two subsets of discontinuities. If I think of it like a Venn diagram, there's the non-removable and there's the removable. Okay? Within non-removable, there's two types of non-removable. There's the infinite, and there's three types. Right? I misspoke. There's an infinite, and there's a jump, and then there's going to be an oscillating. Okay, and the oscillating discontinuity, and I think the easiest way to do this is to show you, right, on a graphing calculator. And here's my graphing calculator. I have the Desmos app on my phone. Okay, and if I were to put in here's an example of one that's an oscillating discontinuity. 1 divided by x. Okay, take a look at what happened there, right in here, and I'm going to zoom in so we can see it better. Right, as we get closer to 1 over x, and I'm sorry. Let's see. Right, there we go. That's working a little bit better. Right, it seems like it's okay, a little too bright. Okay, if you look around, right, the 0. Okay, and I just paused the video to bring down the brightness so we can see it better. There we go. That's better. Okay, if you look around 0, right, and then you can see what's happening there. If you look at this discontinuity, as you get closer to 0, the sign of 1 over x, this is approaching infinity. So what's happening is that your graph is just getting condensed and jammed in there really closely, right? Okay, and let's see if I can get that go away so I can see better. Right, if we zoom in, you can see that the graph in there is just oscillating back and forth very close. So that's the third type of non-removable discontinuity. Oscillating, and you barely if ever see an oscillating discontinuity, right? You don't really have to worry about it too much. Okay, so there's those two subsets. So whenever you have a discontinuity, right, you can basically, I want you to first break it up. Which category is it going to be in, right? And since we know with this graph here, right, it's not removable. Remember, removable is that a point was removed from our graph, creating that discontinuity. Non-removable is anything else, right? You can't fill in a point to make it continuous. So this would be that's why this is going to be non-removable discontinuity. Okay, and then it's also infinite because if you did the graph, you can see that it's going way up. One side's going way up to infinity. If both are going to infinity or both are negative infinity, it doesn't really matter. Just as long as you have one of the two sides approaching infinity, then it's going to be an infinite. So if I was asking for it, a graph would be one way to justify that. Okay, if you don't want to do a graph, right, that's what I talked about in the second one. Okay, right, after you get the discontinuity, Okay, and you can just find the directional limits, and if you do the right side of the directional limit, just like we've been doing, right, when we did some of the limits last week, you would get negative infinity, and once you get negative infinity, that tells you it's a non-removable infinite discontinuity. So right there, that's the justification. So both of those are valid, a graph or the limit analysis there, but you have to have something that justifies the type of discontinuity. Again, if you're trying to justify that it is a discontinuity, you would just say for this one, f of 8 has no solution, and then you'd be done. Okay. If we look at C and we have a piecewise function, first of all, you look at each of these individuals' pieces and just say, are these on their own continuous? And yes, they are. How do I know? I'm thinking about the graph. That's a line. A line is nice and straight. There's nothing special about it. You're never picking up your pencil point. Same thing with x squared. On their own, each of these are going to be continuous. All I have to worry about is that crossover point at 1. Okay, so I calculate the limit as I approach 1 from the left. Okay, I get 2, and when I'm doing from the left, I'm using this top function, and and then I calculate it from the right. When I'm calculating from the right, I'm using the bottom function because of the domain restrictions there, and I can see that those limits are not equal. So that's why this one right here is a non-removable. It's non-removable because the limit does not exist, and then since they're finite values, it's a jump. So you would say it's a non-removable jump discontinuity at x equals 1. Okay? Alright, so that's how you would basically go through and classify the type. Okay? Right? Remember we did sine of x. Right? So when we did sine of x there, right, that was would the limit exist as you approach 0, right? So it's going to be a removable discontinuity, but the actual f of 0 is no solution, so it's going to be a that's why the f of 0 not having no solution tells us it's a discontinuity, right? But since the limit exists, then it's going to be a removable discontinuity. So that's why that one was removable there. Okay. So let's say we're doing one from scratch, and this gives us the answers here. This next one. Okay. But if we're looking at this guy right here, right, I can see that there's a domain restriction at x equals -4. X cannot equal -4. So that tells me there's a discontinuity at x equals -4. So you do that first. If you're asked to justify it, you would just say f of -4 has no solution. Okay? And that would be your justification that there is a discontinuity there. Okay? If you're going to justify the type, I would reduce this. And I got x minus 3. So I can do the limit as that. If I calculate the limit as x approaches -4 of x minus 3, I'll get -7. So right there, because what that tells me is that the two ends came together, but then there was just an open circle right there. So that's why this is going to be a removable discontinuity. Okay, and this right here would be your justification for why it's a removable discontinuity. Okay. Okay, so that's basically what you have to do. If there's multiple points of discontinuity, like if I were to do the reciprocal of that, okay, then you do each one individually. There's two discontinuities, right? So you just kind of say, okay, for each, you do it as two separate problems for yourself, okay, and you look at each one individually there, okay. So, where can we use this? What types of problems? And here would be an example of one where we could use this. Explain why e to the x equals x plus 3 has at least one positive solution. Okay, so one way to do this is I take this, and it doesn't say find the answer, it just proves. It says prove the answer. Okay, and the first thing is we want to first make sure that we know it's continuous. Okay, so what I typically do is I move everything to one side so that it equals 0. Okay. And then I analyze this equation and look at that equation and make sure this equation is continuous. E to the x is continuous. So if we think about that graph looks something like this. Negative x minus 3, that's a line. So basically you have a curve like this for the exponential and then a line, so it's going to be continuous. Okay? That's good to know, and we need to say that, right, for ourselves. In order to solve this, that's the first thing you have to do. We proved it's continuous. Right? And here's why. If I plug in a value of 0, I get negative 2. So that means if I was looking at this graph, the graph of this function, right, it would plot out, so 0, negative 2 was a point. Okay? If I can then get a second point that I know is above the axis, then I can say for certain this is going to equal 0. And that's using the intermediate value theorem. Okay? Right? And you may or may not have used that before. So you always start by saying you have to show that the function is continuous. Okay? And then, right, that's the key. You have to start with that. Okay? And we know it's continuous because it's an exponential on a polynomial. Okay? Then you have to find a negative case and a positive case. So negative 2, right, 0 was a negative case. And I just did that one because it was easy. Okay? And then I plugged in 4. And you can play around with your calculator. I could have tried other values. Maybe I tried 1 or 2 and see if those work first. I did 4 because I knew that this is like 2 to the 4th. So that's like 16 minus 4 minus 3. So that's definitely positive, right? So this right here is some positive number, right? It's greater than 0. Okay? So this right here was less than 0. So if I know at one point it's less than 0, and at another point it's above 0, and I know that's continuous, since it's continuous, these must be connected. And now I don't know how they're connected. It could go like, it could have a swish in it. It could go curve like this, curve like that. It could be a straight line, right? It depends on the function. But the point is that it has to go from here to here without you picking up your pencil point. And since that happens, right, well, then you have to hit the axis at least one value. There could be 1, there could be 3, there could be, I don't know, 2, there could be 5. We don't know, but we know that there's one answer because this is below and that's above. Okay? And this is the intermediate value theorem that we're using. Okay? And that's basically what this says right here. Okay? If it's continuous, you got to start with that continuity part. If it's continuous and there's one value that's negative and another value that's another x value that is positive, then there must be at least one value, right? Right? So, okay. There must be at least one solution. Since I proved that this has a solution, that means that this right here must have at least a solution. And now it was positive, and I did prove it's positive because I went from 0 to 4, right? And so I didn't try a negative one. Okay, it said there has to be at least one positive solution. So I was trying to find x values that were positive there. Okay, that's the intermediate value theorem for yourself.